Okay, we're going to stick with the ladder problem for one more example. But this time we're going to do something slightly different. It's still a 10-foot ladder leaning against a wall, but now the question is, how fast is the angle formed by the ladder and the floor changing when the top of the ladder is 6 feet from the floor? So this is very similar, except we're asking about a different rate this time. So I'm actually going to solve this problem as if we haven't already solved the previous problem. So we're going to start from scratch here, again using dreads. First, we'll make a diagram. In my diagram, I'm going to draw almost the same picture. So here's the wall and the floor. Here's the ladder. We can label the length of the ladder 10 feet. We can go ahead and label the x and, or we'll label the 90-degree angle. We'll go ahead and label the x and the y in case we need those. This is x. This is y. But then there's another thing in here that we should label, which is important to this problem, and that is the angle. The angle formed by the ladder and the floor. So I'm going to label that in my diagram as well. That's this angle right here, and I'm going to give that a name. It's an angle, so I'm going to use theta. All right, so now when I get to identifying and sort of thinking about my rates, again, I am given, I forgot to put it down in the problem here, but it's the same as the previous problem. The rate of change in x with respect to time is 2 feet per second. Okay, so that's base of the ladder is slipping away at 2 feet per second. But now the question is we don't actually care about y any longer. Now we want to know what is the rate of change in theta with respect to time. Okay, so when we select an equation, we want to pick something that, based on this right triangle, but we want to pick some equation that ideally involves just x and theta. Because if I select an equation that involves y, I'm going to have to deal with figuring out what the rate of change in y is. And then I'd have to do the entire problem, the entire previous problem, just so that I could do this problem. And that sounds like a pain in the butt. So what I'm going to do instead is avoid y and just find something that involves x and theta. And 10, because I know the value 10, so I might as well use it. So what I'm going to do is think about my trig functions. Think about all the different trigonometric ratios. What we want is some ratio that involves the hypotenuse and the adjacent side. So if you're thinking back to SOHCAHTOA, what we want is the cosine, right? We're going to do cosine of the angle theta equals x over 10. Okay, so that is cosine of the angle is the adjacent side divided by the hypotenuse side, x over 10. So that's our equation. Now we're going to differentiate it. All right, derivative with respect to time of cosine of theta will equal the derivative with respect to time of x over 10. So the derivative of the cosine function is the negative sine function, right? So we'll do negative sine of theta, but then theta is a variable which is changing over time. So we should think of theta as a function of time. Multiply by d theta over dt. So that's the left side. The right side, x over 10 is like 1/10 times x. So the constant multiple rule tells me I'm still going to have that 1/10. And then I just have to multiply by the derivative of x with respect to time, which is just dx over dt. That's going to equal 2 in the next step. So there is my differentiated version of that equation. So now I get to substitute. So now we're going to substitute in our known values. We're going to put in the 2 for dx over dt. We're also going to need to know theta, though, so that we can get the theta over dt, right? There's 3 unknowns here. I've got to make sure I put in dx over dt and theta. However, actually, figuring out theta is not particularly important. Because if we can figure out what sine of theta is without ever having to figure out theta, then we can get around it. So sine of theta we know is the opposite side divided by the hypotenuse side, right? Sine of theta will be opposite over hypotenuse, which is y over 10. Let's write that down. Sine of theta is y over 10, right? And we happen to know that y is the distance between the top of the ladder and the floor. That is going to be 6 feet, right? It was right here, right? That is the moment in time, and that's the information we were given that was specifying the moment in time. It's when that y is 6. So what we can do here is just say sine of theta is going to be 6 over 10, and that's 6 feet divided by 10 feet. Okay? So I think that is all we need, right? We don't need to figure out what x is because we don't actually need the cosine of theta. We just need the sine of theta. So I think we're good to go. So now, substituting stuff in, I'm going to get negative. Sine of theta is 6 feet over 10 feet. Multiplied by d theta over dt, which is unknown. That's what we want to solve for. And then equals 1/10 times dx over dt, which is 2 feet per second, like that. So now that I've substituted that all in, now it's time for me to solve that. Solve for d theta over dt. So d theta over dt is going to be, I'll have my 1/10 times 2 feet per second, and then times the reciprocal of this fraction over here, because I got to move it over. So it's going to be negative 10 feet over 6 feet. And here's the moment where actually I just realized that I have a little thing I need to fix in here, because in order for me to get my units to all work out properly, I should pay attention to how cosine was being calculated, because this is x feet divided by 10 feet, right? So that means that that 1/10, which is in front of the derivative of x over here, that is actually measured in feet. So this should be in feet down here. Sorry, I neglected that part, but we fixed it now. So now we're going to have 1/10 times 2 times negative 10 over 6. So the 10s are going to cancel out. We're going to have negative 2 over 6. So negative 2, hang on a second. Negative 2, did I miss something? Negative 2 over 6. Sorry, my notes are wrong. I think that's fine. Negative 2 over 6 is negative 1/3. Okay, I'm going to go with it. And then if we check on the units, feet cancel out here, and my units are just 1 over seconds, because we don't have any other feet, right? All the feet cancel out. It's just 1 over seconds. So this is kind of a puzzling answer. D theta over dt is negative 1/3, 1 over seconds. See if you can figure out what should the unit actually be up there. I'll give you a second. Pause the video and think about that. So the answer is d theta over dt is actually negative 1/3 radians per second. And the reason I know that's the answer is two reasons. First of all, as I have mentioned before, when we're doing calculus with trigonometric functions, we should always consider the inputs to our functions as being measured in radians. And the reason for that is because the derivatives that we've learned, like the derivative of cosine is negative sine, that is only valid if your input is in radians. If your input is in degrees, you get a constant multiple in there of like 180 over pi or whatever, or maybe it's the reciprocal. But that's it. So we need to be using radians in order for our derivatives to be correct. And the other reason that this makes sense is that radians are technically a unitless measurement. You may remember that a radian is calculated by taking like it's like a distance measured along the outside of the circle divided by the radius, and those are both length measurements. So it's like centimeters divided by centimeters, or feet divided by feet, or something like that. So technically, when you're measuring something in radians, it doesn't have any units, which is why in this setup here, what we end up with the units is all of the feet canceling out, and our numerator is just 1. All right. So yeah. So there we go. So we solved this one, and we learned a little bit of trigonometry that we either forgot or never learned before, and we had some fun. So. And I accidentally made a mistake on my notes. Sorry about that, but we fixed it in the video.